This video is about the change of base formula, which allows you to calculate logarithms of pretty much anything. So you've got on the first line the formula, but in the example maybe it's easier to understand what the formula is about. So suppose I want to calculate the logarithm in base 3 of 7. So according to the formula, I can calculate instead the log of 7 over the log of 3. And here log stands for log in base 10. In fact, in this formula, it could be the log in any base. Okay, that works, but we're going to typically choose log in base 10. And log in base 10 is usually written just by log. And the reason why we can take log in base 10 is because our calculator is going to have that button. If the calculator doesn't have a log in base 3 button, but it has a log in base 10 button, and using the change of base formula, we can calculate a log in any base using a log in base 10. So I will give you why we would want to calculate or log in base 3 of 7. Why would we want to calculate it using log in base 10? Well, it's because if you think about it for a second, when we're calculating a log in base 3 of 7, right? Let's say x is our unknown, log in base 3 of 7. If I write this in exponential notation, it means that 3 raised to the power x, because the logarithm is a power, right? So 3 raised to the x is going to give me 7. And this is not an equation I can actually solve easily, since 7 is not a power of 3, so I cannot have equal base on both sides and equate the exponents. That's not going to work. So obviously x is going to be some number that's not an integer or nothing nice really. Probably some sort of decimal number with an infinite amount of decimals that do not repeat themselves, so probably an irrational number, in fact. So having the change of base formula will allow me to calculate what that x is. So I will finish this video with 2 examples, okay, of problems where we'll be using it. But before that, I thought I'd give you a proof of the result, and we're just going to start with that. And the proof starts with a basic property that we know holds for logarithm. It's basically based on the kind of silly exponential equation. B to the x is equal to b to the x, right? That's obviously true. But if we look at it from the perspectives of logarithm, right? And let's look at this x. So x here is the power. So if x is a power, it's a logarithm. So it's the power to which we raise b in order to get b to the x. And then we get this identity, log in base b of b to the x is equal to x. All right. Okay, so that also means I wrote x, but it could be y, right? So any number, okay, is equal to the log in base b of b raised to that number. Okay, so I could write down any letter. So what I'm going to do now is rewrite not b to the x, but I'm going to raise b to the x to the r. Okay, now b to the x to the r, we know using rules of exponents that this is b to the x times r. Okay, so that's going to be kind of like my y. It's some number, right? X times r, some number. According to this equation here, this is equal to y, to x times r. And actually I'm going to write it as r times x. Okay. But x, this is where I'm going to use this guy, it's also equal to log in base b of b to the x. Okay, so let's look what we have. I've got this thing here. and I've got this thing here. They're both equal. And look at the r here. It used to be as an exponent here, and now it's shown in front of the logarithm. So in some way it has migrated here. And so this is a property of logarithms that I've just established here, okay, based on essentially properties of exponential exponents, right? And we'll see that later in the follow-up to this course, that a lot of properties of exponents essentially translate to properties of logarithms. So this is, so I'm going to write this. We have that log in base b of b to the x to the r is r log in base b of b to the x. Now, b to the x is going to be some number. Okay, let's replace b to the x by m. Okay, and here you'll have to trust me, but if b is some positive number, if I raise it to any power, okay, x, it's going to generate essentially numbers that are positive, okay, ranging from as close as I want to 0 to infinity. So m here could, like, since m is going to be equal to b to the x, it varies between 0 and infinity. So it covers a wide range of numbers. This is what I actually mean here. So if I replace b to the x by m in the equality above, okay, I'm going to write m to the r here. So log in base b of m to the r is r log in base b of m. And this is an important identity that essentially states a property of logarithms. Okay, and I'll just give you an example. If we've got log in base 2 of 8, okay, what is that equal to? Well, that's the power to which we raise 2 in order to get 8. It's not too hard to see that it's 3, okay, since if I raise 2 to the 3, I'm going to get 8. But let's take another look at this. 8 is actually 2 to the 3. And according to this rule here, okay, the 3, I can actually send it in front of the log. So I get 3 log in base 2 of 2. And now what's log in base 2 of 2? Well, 2 to the what will give me 2? 2 to the 1. So log in base b of b, okay, no matter what the b is, as long as it's positive, will always give you 1. So log in base 2 of 2 is 1. So this is 3 times 1, and we get 3 again. So you see there's no contradiction here. I've evaluated log in base 2 of 8 using the two possible ways that are stated in the identity I've just established here. Anyway, so all this to say that this identity is going to show up in my proof. So I'd like to calculate log in base b of a, and I'm going to call that x, okay? And the first thing I'm going to do is rewrite this as an exponential equation. It means that x is the power to which I raise b in order to get a. Now I'm going to take log, so by log I mean log in base 10, okay, because I just write log on both sides. So the two, if b to the x is equal to a, I can take the logarithm of each, right? Those are two numbers, and logarithm of each side, since it's the same number, will give me the same number. So essentially, log of b to the x is log of a. So I've applied essentially the same operation on both sides. I'm taking logarithms of the exact same thing. Now, look what I'm going to do now. I'm going to take this x here and put it in front. This is according to the property of logarithms I've just established. So x log in base b times log in base b is equal to log in base a. So this is a multiplication here, right? And finally, to solve for x, I'm going to divide by log in base b. and I get this. And finally, I'm going to go back and remind myself that this x here is log in base b of a, so we'll replace x by log in base b of a, and I'm going to get log in base b of a is log of a over log of b. And in my proof, so that establishes the formula. And in my proof, I took logs here in base 10 on both sides. I could have taken log in base c. Okay, so this formula is also true for any base. Okay, it could be log in base 3. Okay, if I had a log in base 3 button on my calculator. But usually, like I said, we're going to use log in base 10 because that button exists on my calculator. So that's the end of the proof. I'm going to give you two examples where I'd be using that formula. So I want to solve 7 to the x equals to 13, this exponential equation. What I'm going to do is translate that into a logarithmic equation. Okay, so x is the power, so it's a logarithm. A logarithm's a power to which I raise 7 in order to get 13. So I need to calculate log of 13 in base 7. But now, according to my change of base formula, this is log of 13, and so log in base 10 of 13 over log in base 10 of 7. Okay, so that's it. That's going to be my answer. So let's, I've got a little scientific calculator that I can use here. Oh, as you can see, I was watching Roger Federer do some amazing serves. Let's switch to the scientific calculator. This is, I want to calculate log of 13. I'm going to close my bra. Okay, and I'm going to divide this by log of 7. And that's going to give me 1.318 approximately. So I'm going to write that down. So this is approximately 1.318. And if you don't trust your answer, you could always go back. I could actually replace, if I replace x by 1.318, and there I should be getting that 7 raised to that value should be pretty close to 13. Not exactly, because I've rounded my answer here, but it should be pretty close. Let's take a look again at that. Here we go. So I'm going to clear this. So I'm going to do 7 to the, I said 1.318. And look at the value that it's giving me, 12.996. You see it's pretty close to 13. So you can always verify that your value actually works by plugging back your value into the original equation. So this is our first example. Second example, we're going to solve. This equation is a bit more complicated. This is still 7 to the x equals 3 times 6 to the x plus 1. So my goal is to write this as, eventually, as in terms of an exponential equation of the form b to the x equals c. Okay, so this way I can translate it into a logarithmic equation afterwards. Okay, and then use the change of base formula. So this is what I'm aiming for. So first thing is, I'd like to have things raised to the power x. Okay, so what I'm going to do, I've got 7 to the x, which is great here, but 6 to the x plus 1, I want to convert that so that it ends up being something to the x. So now I'm going to use a property of exponents. So 6 to the x plus 1 is 6 to the x times 6. So that's the product rule here. So I've got 7 to the x, 6 to the x. I'm going to try to regroup those together. And that's 3 times 6, 18. And finally, 7 to the x over 6 to the x. That's the same thing as 7 over 6 to the x. And now I'm at a point where I've got an equation of this type, b to the x equals c. And now I'm going to rewrite this in terms of a logarithmic equation. So x is the power to which I raise 7 over 6 to get 18. Now I'm going to use my change of base formula. This is log base 10 of 18 over log and base 10 of 7 over 6. Let's try that. So let's clear this. Log of 18 divided by log of 7 divided by 6. And we get 18.750. Let's rewrite this here. So 18.750. Once again, you could go back and replace your x by that value and make sure that it works. You'll see that it does. So this is our final answer. And that's it.